Hello students, welcome to the amazing platform of PW English, my dear students. So today we are going to cover our lecture 3 of solutions chapter. Till now we have discussed about concentration terms, what are the different types of concentration terms and how the questions would be made out of those concentration terms. Today we are going to start actually what is the most important part of solutions. Yes, so let's start, my dear students. This doesn't mean that concentration terms is not important. It is equally important. I am just telling you that we are actually going to start the solutions chapter. So for solutions chapter, what are we going to discuss first? So my dear students, we today are going to cover solubility. The first and the most important topic is solubility. Just a second. Yeah, so we are going to cover solubility. What is solubility? Now we know that a solution consists of at least two components, one solute and one solvent, right? Yes. And for a solution to be homogeneous, there should be solubility. Today we are going to understand the term solubility first, and then we are going to talk about the Henry's law. It is very important topic because a lot of questions are asked from this. And my dear students, like always, at the end we are going to practice a lot of questions. So you all have to be very thorough with the lecture so that you can cover all the questions. So now let's start the amazing session. Okay, yeah. Now, my dear students, what are we going to discuss? We are going to discuss about solubility. What is solubility? Let's take an example. Imagine you might have seen sugar syrup. Every child has seen sugar syrup, right? Yes. So how is it made? What is the solubility? Now we are going to understand that. So now, my dear students, imagine you have water and you are adding sugar to it, right? Yes, you're mixing it. Yes, ma'am. You mixed at a particular temperature. Now imagine if you have a container, and you have water inside it, and you are actually adding sugar to it, right? Yes. Now all this is actually taking it let's say I am performing this experiment, so I'll be in a particular room. There will be a particular temperature fixed, right? Yes, the temperature might not be changing. Yes, so the condition which is important here is that temperature should be constant. That temperature should be constant, right? Yes, perfect, no issues. Now, as long as at the same temperature you are mixing the sugar, you'll mix sugar, you'll add sugar. At one point, a point will come at this particular temperature that no more sugar you can dissolve in the solution, in the solvent, that is your water, right? Yes. This means that for every solution which has at least two components, there is a maximum limit, the amount of solute you can dissolve in a particular solvent, right? Yes. And that is what is known as solubility. What is that solubility? From here we can say that solubility it is the maximum amount of solute. It is the maximum amount of solute that can be dissolved in a solvent at a particular temperature T. Now imagine I want to add more sugar. I right now want to add more sugar, but the solution is not allowing me, right? Yes, because it has came to its maximum limit. Now if I heat that solution, and I try to add the sugar, I try to dissolve the sugar, it will be dissolved. This is what is happening here, that you are actually not taking temperature now constant, you are increasing the temperature. On increasing the temperature, solubility has increased. Okay, fine. But as long as the temperature was constant, there was a limit of amount of solute that can be dissolved in a particular amount of solvent, right? Yes. So it is the maximum amount of solute that can be dissolved in a particular amount of solvent, in a fixed amount of solvent, fixed amount of solvent. Okay, at a particular temperature T. Now the question comes that solubility depends on what all? What all are the things on which solubility depends? So now we are going to understand that concept. So now, my dear students, imagine you had water and you had sugar, so you calculated some solubility, right? Yes. If you had not water but something else, some other solvent, right? Yes. Let us say you had alcohol, right? Yes. Now you'll add sugar, then, my dear students, there will be some other fixed amount at some particular T temperature, that the amount of sugar that would have been dissolved. This means that this means that how you are changing your solute solvent, your solubility is changing, right? Yes. So this means that solubility actually depends on the nature of solute, that is, what solute are you taking. You can take sugar, you can take salt. Every solute will have a fixed solubility, right? Yes. So it depends on the solute, it depends on the nature of the solute. If you change the solvent, the solubility will change. So this means that solubility depends on the solvent's nature as well. You change the temperature, solubility changed. This means that solubility depends on temperature as well. Similarly, if you change the pressure, solubility will change. This means that the pressure around you, if you will change the pressure, the solubility will change. This means that solubility actually depends on four major things: nature of solute, nature of solvent, temperature and pressure. So let's write it. Solubility depends on nature of solute, second is nature of solvent, third is temperature, and fourth is pressure, right? Yes. So fourth would be pressure. Perfect. So these are the four factors on which solubility depends. If you change any factor, solubility will definitely change. So this is the major thing that we need to understand about solubility. So I'll move aside and you can write this. Okay. I hope you've written it. Now let's move forward. Now, my dear students, we've understood that what is solubility and on what all factors does solubility depend. Now, you might have heard of a concept that like dissolves like. Now, let's understand that concept. So now, my dear students, I have salt. I have NaCl. Okay. If I dissolve salt in water, these are soluble. So I'll write it that they are soluble. Okay. No issues, no issues. Now there my salt is solute and my water is solvent. Now imagine, my dear students, what if I think of dissolving NaCl, that is my salt, in benzene. Let's take solvent as benzene, right? Yes. So if you have benzene as your solvent, and you will have NaCl as your solute. So now my question to you is, are they soluble? Are they soluble? No, my dear students, they'll not be soluble, right? Yes. So they are not soluble. Why? Why does this happen? So now we are going to understand this, because, my dear students, we know a concept which is like dissolve like. Now let's understand this. What does this mean? Like dissolves like. So now, my dear students, like dissolves like means, if you think about yourself as well, you have friends, and generally the people with the same interest are friends, right? Yes. If I have a friend, definitely we like something together, right? Yes. But if somebody is totally opposite to you, your likes never match at any point. Can you be friends with them? No, you cannot be friends with them, right? Yes. We generally get along with the people who are like us, right? Yes. This means that like you want some people to be like you, right? They should have the interest like you. Same way, your solute and solvent actually wants that they should have nearly same intermolecular forces, so that they can be soluble into one another. So for solubility, my dear students, you generally check whether a solute and a solvent are polar or non-polar. Polar things will definitely try to dissolve in be soluble in polar solvents or polar things, right? Yes. So this means that polar solute will dissolve in polar solvent and non-polar solute will dissolve in non-polar solvent. Now imagine here what happened. You had NaCl and NaCl is polar in nature. You've studied this in chemical bonding, and that is the reason I'm not explaining here. Polar and non-polar nature is actually what you study in 11th in chemical bonding. Okay. So NaCl is polar in nature. Similarly, H2O is also polar in nature, and that is the reason polar like dissolves like, so that is soluble in water. Okay. Now I know that NaCl is polar, but my dear students, benzene is non-polar. And that is the reason they both are not soluble. That is the reason your salt is not soluble in benzene, because it is not like, they are not same. If I say that I want to dissolve naphthalene in benzene, then my dear students, they will be soluble. They will dissolve, they will be soluble. Why? Because this time, my dear students, naphthalene is non-polar in nature. And similarly, your benzene is also non-polar in nature, right? Yes. So I hope you've understood that the nature of your solute and solvent actually defines that will they be soluble or not, right? Here, this was your solute, this is your solvent, then nature actually defines whether it is soluble or not. So here we have studied these two parts, that what is the nature actually defines that will they be soluble or not, right? Yes. Next is, my dear students, temperature. So now we are going to talk about the effect of temperature on solubility. Okay, before that I want to just tell you that what is a saturated solution. Sometimes in chemistry you come across a term which is known as saturated solution. What is a saturated solution? Let's write it here. Saturated solution. What is a saturated solution, my dear students? A saturated solution is a solution where at a particular temperature. Now imagine the example I gave you of sugar syrup, right? Yes. You had a particular amount of water, you dissolve the sugar into it, and the maximum amount reached, right? Yes, at that particular temperature. No more solute was able to be dissolved. At that point, my dear students, that state of that solution is known as saturated solution, which means that a saturated solution is actually a solution where no more solute can be added, to that solution at a particular temperature T. Okay, so saturated solution, it is a solution in which no more solute can be dissolved at a particular temperature T. Right? Yes. So this is how you are going to understand the saturated solution. A very basic term which you will come across a lot of times. So I just told you. Okay. Yes. Perfect. Now let's study another important part, which is the effect of temperature. How does temperature affect the solubility? Right? Yes. So now, my dear students, what I want to tell you is, I just told you that solute gets dissolved into solvent and you get a solution, right? Yes. So this is what actually happens. You have a solute, you add the solute to a solvent, and you get what? You get a solution. This is the part you know. But my dear students, I just want to tell you that in a solution, at a particular point, a state is reached where what happens? This and this actually are in equilibrium. So my dear students, what do I want to tell you is that the amount of solute and solvent mixing and forming solution, and the solution getting converted into solute and solvent, that process is dynamic, and that is how an equilibrium is reached. This is what actually happens in a solution, right? Yes. But we cannot see it. It is a dynamic equilibrium. Okay. So this is very clear to you. Now, my dear students, you might have studied thermodynamics, right? Yes. You might have studied thermodynamics, and my dear students, in that you might have also studied that what are endothermic reactions, what are exothermic reactions. If you don't know, don't worry. I am here. I'm gonna tell you. Okay. Yes. One more important thing, when you studied in equilibrium, you studied a concept which was the Le-Chatelier principle. So now we are going to combine all the parts, right? Yes. So I am smiling because I know you all are like, ma'am, we don't remember, right? Yes. So don't worry, I am here. I'll tell you each and every part. So one by one, we'll move forward. First and the most important thing is, what is Le-Chatelier principle? So now, my dear students, Le-Chatelier principle is actually when you have a equilibrium, let us say you have a reactant and it is in equilibrium with a product. Okay. Yes. So you have an equilibrium attained. Now what happens is you tried to change this equilibrium. You tried to disturb this equilibrium. How you try to disturb this equilibrium? Now, how can an equilibrium be disturbed? Might be you tried to increase the product. Right? Might be you try to increase the reactants. If you try to increase the amount of product or reactant, the equilibrium will get disturbed. Right? Yes. Now, what does Le-Chatelier principle say? Le-Chatelier principle says a very simple thing, that if you are going to try to disturb my equilibrium, I'll definitely do the opposite of what you want. This means that you actually tried, let us say for time being, you tried to increase the products. Okay, you added more of the products in the equilibrium and you tried to increase the amount of products. Now, Le-Chatelier principle says that this person actually tried to increase the product's concentration. I should do something and decrease the product's concentration, right? Yes. So what will it do? What is the maximum it can do? It will shift the reaction backward. And if the reaction shifts to backward, that means that now the products will be consumed and you will get the reactants as products, right? Yes, I hope you're getting this concept. So what does Le-Chatelier principle do? It doesn't do anything. It just tries to do what you are trying to do, opposite of that, right? Yes. I hope this is clear to you. Le-Chatelier principle, whatever you will do, it will do opposite of that. Perfect. If you try to disturb the equilibrium, it will again do what you want. It will do opposite of what you wanted, right? Yes. This is Le-Chatelier principle. Now, the next two concepts which I told you were endothermic and exothermic reactions, right? So now let's talk about endothermic and exothermic reactions. So my dear students, what does endothermic reaction means? And endothermic reaction means that you are actually trying that a particular reaction takes place and heat is absorbed. In an endothermic reaction, a particular reaction takes place and heat is absorbed. And if you talk about an exothermic reaction, a particular reaction takes place and the heat is evolved. Okay, so these are the concepts. I'll apply in these and you will understand very clearly. Don't worry. Okay, so now let's start. There are two possibilities. If you're trying to make a solution soluble, if you're trying to make a solution, right, if you're trying to dissolve a solute into a solvent, yes, then what will happen? Two possibilities, ma'am. Either the reaction could be endothermic or the reaction could be exothermic, right? Yes. So let's take both the examples. If the reaction is, let's take the example if the reaction is exothermic, and the second is reaction is endothermic. Okay, now let's talk about one by one each. Try to do the first part, understand this from my side, and then try to do the second part yourself. Okay, if I talk about exothermic, what does exothermic mean? Ma'am, exothermic means that heat is evolved. Okay, so I'll write heat. First I'll write delta H here. Sign is actually negative. Here the sign is actually negative. Okay, and now my dear students, in this case heat is evolved. Now if heat is evolved in a reaction, then what will happen? What will happen, my dear students? You will have solute, you will have solvent, and there will be a equilibrium. You will have solution. Now, since in an exothermic reaction heat is evolved, so the heat will be on the solution side because heat is evolved. So heat will be here in an exothermic reaction. Okay, yes. Till now you're very crystal clear with the concept. Now what I want to tell you is this. You are actually in an exothermic reaction, you want to see the effect of temperature. So imagine you are trying to increase the temperature. If you increase the temperature, what are you doing? Ma'am, we are trying to increase the temperature, and temperature actually increases the heat as well, right? So if you are increasing the temperature, you are trying to increase the heat. So this means that you are trying to increase the heat. If you are trying to increase the heat, my dear students, what are you doing? You are disturbing the equilibrium. You are trying to increase the products, right? What will Le-Chatelier principle do? Ma'am, Le-Chatelier principle will say you are trying to disturb the equilibrium and you are trying to increase the products concentration. I'll decrease the products concentration and the reaction will move backwards, right? Yes. So I can say that reaction moves, or I would say equilibrium shifts backward. Okay. I hope this is clear. You are trying to increase this side, the Le-Chatelier principle will take the equilibrium backwards, right? If you will take it backward, what will happen? What will happen, my dear students? If the reaction is this side, is the solubility increasing? No, ma'am. More of the solute and solvent are separating out. This means that solubility is actually decreasing. Solubility is actually decreasing. So don't memorize it. Try to understand the concept. Very clear concept. Very easy. You're increasing the temperature. You're trying to increase the heat. You're trying to increase the heat. You're trying to increase the product concentration. The equilibrium will shift backward because of the Le-Chatelier principle, and moving backward means that the solubility is actually decreasing, right? Now, let's take the other way around. If you try to decrease the temperature, heat will decrease. This means that what are you doing? You're trying to decrease the heat. This means that you're again trying to disturb the equilibrium. But this time you're trying to disturb the equilibrium by decreasing the product's concentration. And if you're trying to decrease the product's concentration, Le-Chatelier principle would say that if you're trying to decrease the product's concentration, I'll move forward and increase the product's concentration. So this time equilibrium shifts forward. Now, if the equilibrium is shifting forward, this means that the equilibrium is shifting forward, this direction. This means that solute and solvent are forming more of your solution. And this means that solubility is actually increasing. This means that solubility is actually increasing, right? Yes. So this is very easy, very easy. You don't need to memorize it, right? Yes, you can understand this concept. If you've understood this concept, now let's start for endothermic, right? For endothermic, my dear students, what happens is, again, you have for endothermic reactions, delta H is always positive, and here heat is absorbed. Heat is absorbed. So if heat is absorbed, this means that you have solute plus solvent which will give you solution, right? Yes. Now, my dear students, where will the heat come? If the heat is absorbed, this means that the heat will be on the reactant side. Okay, perfect. I hope it is clear. Now, again here, my dear students, the effect could be both. You could also increase the temperature, you could also decrease the temperature. Now again, let's start. If you try to increase the temperature, right, you're trying to increase the temperature. If you're trying to increase the temperature, you're trying to increase the heat. If you try to increase the heat, what will happen? This side will increase. This means that you're trying to increase the reactant side. Le-Chatelier principle would say, you're trying to disturb the equilibrium, increasing the reactant concentration. I'll move forward and I'll consume more of the reactants. This means that equilibrium will shift in the forward direction. So equilibrium forward. If the equilibrium is in forward direction, my dear students, what means? It means that more of the solution is formed. This means that solubility is increasing. Oh, nice. So solubility increases. Easy? Very easy. Let's start the other part. If temperature decreases. If temperature decreases, you are trying to decrease the heat. If you try to decrease the heat, what will happen? You are trying to decrease the reactant side. Le-Chatelier principle, equilibrium will shift in the reactant side, will try to increase the reactance. This means that equilibrium will shift backward. And if the equilibrium will shift backward, this means that solubility will decrease. So here solubility decreases. I hope you don't have any issue with this. This was the most important part from which generally the questions are asked. So try to understand this concept and don't make any errors. Don't try to memorize it, mug it up. Try to understand this concept. Okay, so it is all here. You can write and then we'll move forward. I'll have some water and then we'll move forward. Okay, let's move forward. I hope you've written it. Now, what I want to tell you is, okay, now we've studied the effect of temperature. Now we are going to study the effect of pressure as well, right? Yes, there were 4 factors. We have studied 3 factors. Now we are going to study the 4th factor, which is the effect of pressure. How are we going to study that? So now, my dear students, you all like cold drinks? I think most of the students actually like cold drinks, right? Yes. So what is cold drink? When you taste it, you feel the taste of a fizz, right? Yes, you feel the taste of a fizz. And many of you also know that it has some gas in it, right? Yes. So now, my dear students, what I want to tell you is that when you consider a solution where your solute is a solid and your solvent is water, liquid, right? Yes. Pressure does not have a lot of effect on it. Pressure does not have a lot of effect on it. If you're trying to mix, if you're trying to mix any solid into a solvent, into a liquid solvent, pressure doesn't play a very important role. It has very negligible effect, right? Yes. But if your solute is a gas and your solvent is a liquid, then pressure has a very important role to play. Okay. So for gas, all other concepts are same. Right, only the pressure factor is changing, because for solute, when you have a solid solute, pressure does not play a very major role. It is nearly negligible. But for a solute as a gas in a liquid, it has some effect. So now we are going to study that. Okay. So now how I want to make you understand is, you all like cold drinks, right? Whenever you open the cold drink bottle, what happens? All the cold drink comes out. All the cold drink comes out, right? Yes. If you open that bottle, all the cold drink will come out, right? Yes. So now what I want to tell you is, imagine you opened a fresh bottle. You'll taste that cold drink and it will taste amazing, right? Yes. Now keep it open for let's say half an hour, okay, and then try to taste that cold drink. It will taste like some sweet solution, right? Yes, it will be some sweet sugar syrup type. The fizz would have gone. Same is for sodas, right? Yes. What actually happens here is, my dear students, that in cold drinks, what happens is you have gas dissolved in liquid. Gas dissolved in liquid, right? Yes. In cold drinks, you have gas dissolved in liquid, and when you open the bottle and you drink it at the very fresh start, you taste a fizz, and that taste of fizz is because of the gas. Now, if you keep it open for a while, the gas escapes, and then you just then the liquid actually just tastes as sweet solution, right? Yes. The fizz taste has gone. Why does this happen? The question is, why does this happen? Now we are going to understand this, because this has something to do with the pressure. And who told this part? My dear students, there was a scientist, Henry, who told us that pressure plays a very important role if you want to dissolve a gas in a liquid. So now we are going to study about that. Okay, perfect. Let's move forward. So we are going to study the effect of pressure. So now, my dear students, what I want to tell you is, imagine you have a container. And you have some liquid here. And you have some gas here. Okay. Now what happens is, you apply pressure here. You apply some pressure here. Okay. You will try to pressurize it. What will happen? The gas will get dissolved in the liquid. So I can say that this is liquid and this is gas. Okay. Yes. So in this way we can say that as the pressure is increasing, more of the gas is getting dissolved in the solution. So more the pressure, more will be the solubility of gas, right? Yes. So from here, can I say that more is the pressure and it will be directly proportional to the mole fraction. Now ma'am, why mole fraction? I'll make you understand that as well. Now my dear students, imagine you have applied some pressure and some amount of solute has dissolved in your liquid. Let us say the volume is V ml. Okay, let us say the volume is V liters. Why volume? Let's say amount. Let's talk about moles. Let's say you have X moles here, okay, of your liquid. So the amount of liquid is fixed. Okay. So now my dear students, the pressure you will apply, the more amount of your gas will be dissolved in this X moles of solute. Yes, ma'am. Sorry, solvent. Yes, ma'am. This way, I can say that the more the pressure I apply, the more will be the mole fraction of the solute in it. Yes or no? Imagine, let's say you have 2 moles of this first, then you will have 3 moles, then 4 moles as you increase the pressure. So now, my dear students, if you see mole fraction of solute, which means that moles of solute upon moles of solute plus moles of solvent, right? Yes. Imagine, if you are increasing the moles of solute, my dear students, your whole this factor will increase by a little bit, but since, how can I make you understand this? Imagine moles of solute upon moles of solute plus moles of solvent. Okay, yes. Now you know that always whenever you take a solution, you generally take a very dilute solution. Okay, so you take a dilute solution. I'll tell you dilute solutions. We generally talk about dilute solutions. So if we are talking about dilute solutions, which means that the moles of your solvent are very much more than the moles of solute. Right? Yes. So ma'am, here moles of solvent will be very much more than the moles of solute. So I can say that moles of solvent plus moles of solute will be nearly equal to moles of solvent. I can neglect the moles of solute as compared to moles of solvent because it is a dilute solution. Dilute solution means that you have a very large amount of solvent, right? Yes. So this way I can say that mole fraction of solute will be equal to moles of solute upon moles of solvent, right? Yes. Now my dear students, imagine. Now you have to imagine that as you are increasing the pressure, more of your solute is getting dissolved, right? Yes. So with time, this factor is increasing. But is your solvent moles changing? No, ma'am. Solvent moles are constant. Solvent moles are constant. So if your moles of solute are increasing, then mole fraction of solute is also increasing. Yes. So this is what I want to tell you. This is what I want to tell you, my dear students. As you increase the pressure, the mole fraction of your solute, that is your gas, is increasing in the solution. And my dear students, here I can write this mole fraction of gas because my solute is gas, right? Yes. And my dear students, this particular part is only known as the solubility. So solubility here is denoted by mole fraction of gas. So the more the pressure you apply, the more will be the mole fraction of the gas, right? Yes. And the more will be the solubility. I hope you've got this concept. Now, my students, this pressure is actually the partial pressure of gas. This pressure is actually the partial pressure of gas. Now, you have to understand it. Try to understand it. If you don't want to understand, then you can only think of that as we increase the pressure, the solubility increases. But actually, the partial pressure of gas actually means that if you ever talk about the closed container, the pressure here and the pressure here, both are actually equal. So inside this part is the partial pressure of the gas and outside is the pressure you are applying, right? Yes. So the pressure which you are applying is always equal to the partial pressure of the gas. But when Henry gave the expression, he gave this expression as partial pressure of the gas. Okay. So you can understand it by the partial pressure of the gas, or you can understand it by the pressure applied. It is equal, right? Because there has to be a equilibrium between both, only then this actually stops here. Okay. So now I hope you've got the Henry's concept, which was partial pressure of the gas is directly proportional to the mole fraction of the gas, and this mole fraction was actually the solubility. The more the partial pressure of the gas, the more will be the solubility of the gas, right? Yes. Now, if you want to remove this proportionality, you will have to add a proportionality constant. So this proportionality constant was given as KH, and here my dear students, this was your actual expression for the Henry's law. Here what denotes, let's write this. P of gas is actually your partial pressure of gas. What is it? It is your partial pressure of the gas. What is KH here, my dear students? Since Henry gave this expression, obviously he gave this constant his name, that is your Henry's constant. So this is your Henry's law constant. And what is X of gas? This is actually the mole fraction, or you can say it is the solubility, right? Yes, this denotes the solubility of the gas. I hope this is clear to you. I hope this concept is completely clear. Very easy, my dear students, nothing to worry about. The more you will apply the pressure, the more will the gas be soluble in it. So the expression was given by this, the proportionality was removed, you got the proportionality constant, which was Henry's constant. You can write it and then we'll move forward. Okay, I hope you're clear with this concept. Now let's move forward. So here is the Henry's law. See, Henry's law describes quantitatively the effect of pressure on the solubility of gas, the effect of pressure on the solubility of gas. See, the more you will increase the pressure, here only W1 pressure, so only a little of the gas was soluble in liquid. The more you will increase the pressure, the more the gas will be soluble, and since the gas is soluble, the more will be the partial pressure of the gas, right? Yes, perfect. I hope this is clear. Now let's move forward. Now, my dear students, we are going to talk about KH. Okay, first let's study about KH and then you can write the factors. Now, we have to study a little about the Henry's constant. What is Henry's constant? Because most of the numericals, which are complicated questions, are generally asked from this part. Okay, so now let's talk about the Henry's constant. Okay, so my heading would be Henry's constant, which is KH. Okay. So now, the first thing that we need to understand is that on what factors does your Henry's constant depend? Does it depend on the pressure applied? Does it depend on the solubility? No, because it is a proportionality constant. So we can say that it is independent. It is independent of P of gas. It is independent of solubility of gas. So it doesn't depend on these two factors. I hope this is clear with you. Now let's move forward. What all does it depend on? Now, what are the factors that it depends on? So now we are going to write that KH depends on majorly two factors. First is temperature. And the second is nature of gas. Now let's understand this. It majorly depends on two factors, which is the temperature and it depends on the nature of the gas. As long as, my dear students, the temperature is constant, KH value will be same for one particular gas. If you have different gases, let us say you have CO2 gas, you have N2 gas, then CO2 will have its Henry's constant, N2 gas will have its own Henry's constant. So Henry's constant is different for different types of gases, which means that it depends on the nature of the gas. Understood? Second, at a particular temperature, KH value will be constant for that particular gas. If you increase the temperature, KH value for that particular gas will increase, which means that KH depends on the temperature of the gas. Okay, temperature of the whole setup. Perfect. So KH actually depends on these two factors. Okay. I hope this is clear. Now you can read this. KH doesn't depend on pressure, but it depends on the temperature, nature of gas and nature of liquid. Yes, and for every particular gas you have a particular KH value. The greater the Henry's law constant of the gas, the lesser is the solubility. Now you're not going to understand this part. This part I'll make you understand now. Now, my dear students, imagine whenever you will try to dissolve a particular gas in a liquid, what will you try? You will obviously you will obviously perform that experiment at a particular temperature, or the temperature will be changing. No ma'am, we'll obviously do an experiment at a particular constant temperature and a constant pressure, right? Yes. So imagine I am in this room and there is some P pressure, right? Yes, some P atmospheric pressure is being applied here. So now, my dear students, if I am trying to dissolve a gas in a liquid, then the pressure is constant, right? Yes, the pressure is not changing. Yes, ma'am. So if the pressure is not changing, then what will happen? Imagine you have the Henry's concept as P is equal to KH into mole fraction of gas, right? Yes. Generally, or I can write that at constant P pressure. So generally, my dear students, pressure for a particular incident is constant, right? Yes. So if the pressure is constant, what will happen? Now imagine you have 16 value, right? Yes. So 16 is 4 into 4. I hope you don't have any issue with it. Yes. If you have 16, which is 4 into 4, imagine you want to keep this part constant, which means that, ma'am, this will be 16. But what am I doing? This is your A, this is your B. What am I doing? I'm increasing A. I want to increase A. I'll say, let us say I increased A by 8. Okay. If I want to keep this part constant and I have increased A, then I'll definitely have to decrease B. Only then I will get 16 value, right? Yes. So this means that as long as the product of two variables is constant, one has to increase and the other has to decrease, right? They will be inversely proportional to each other. So at constant P pressure, KH is inversely proportional to solubility of gas, right? I hope this is clear with you. As long as your pressure is constant, your KH will be inversely proportional to the solubility of the gas. That is, if you increase the KH value, the solubility of gas will decrease. I hope this is clear with you. I hope there's no issue with that, right? Yes. Perfect. This is clear with you. Now I know that KH depends on two major factors. Yes. First is temperature. So what will happen if at a particular pressure P, which is a constant pressure, you try to increase the temperature? If you try to increase the temperature, my dear students, what are you trying to do? You increase the temperature. I told you KH depends on temperature. The more the temperature, the more the KH value. So ma'am, Henry's constant will increase. If Henry's constant will increase, then solubility will decrease. So ma'am, solubility will decrease. Right? I hope this is clear with you. I hope you don't have any issue with it. If you decrease the temperature, your KH value will decrease and your solubility will increase. Okay? Yes. This is clear. Now let's talk about the nature of gas. Second factor is your nature of gas. See, if a gas, you might have studied in states of matter that a gas is liquefiable or a gas is less liquefiable. A gas which is more liquefiable, definitely it will dissolve in a liquid very easily, right? That is, its solubility will be more, right? Yes. So now we are going to use that concept, my dear students. You have studied about A, which is a van der Waals correction constant. For different gases, you have different A values. And the more the A value, the more will be the solubility, the more liquefiable will that gas be, right? Yes. This means that if you have a A value for a particular, every gas has a particular A value, okay? The more the A value, more easily liquefiable gas. Now, my dear students, imagine if a gas is more liquefiable, means that the gas can be dissolved in a liquid, or the gas is easily converted into a liquid. So the more the A value, the more easily the gas can be liquefied. The more will be the solubility. And if the solubility is more, then the Henry's constant will be less. And if the solubility is more, the Henry's constant will be less. So this is how you generally compare the KH values and the solubilities of different gases. Many a times you will be given questions where you will be given Henry's constant values and you will be asked the solubilities trend. So you need to understand the concept and then you can solve all the questions, right? Yes, I hope this is clear with you. Perfect. So you can write all this part and then we'll move forward, okay? You can write this and then we'll move forward. You can write this. Okay, now read this. KH does not depend on pressure, but it depends on temperature, nature of the gas and the nature of the liquid. We are clear with this concept. The greater the Henry's law constant, the greater the Henry's law constant, that is the more the KH value of the gas, the lesser is the solubility. I hope now it is clear that why the solubility is less, because generally we talk about the constant pressure conditions. Okay, let's move forward. Now you have to plot a graph. Graph is very easy. You don't have to do a lot of things. What is the graph? See, you know that Henry's constant P of gas is directly proportional. P of gas is equal to KH into mole fraction of gas. If you know a little about the graphs, then a straight line graph is y is equal to mx, which is a straight line passing through the origin, right? This expression is for a straight line passing through the origin. So the plot will be something like this. The plot will be something like this. Okay, y-axis you have P of gas, x-axis you have mole fraction of gas, and slope will be KH. I'll write here as well, right? Yes, so you have y-axis, you have P of gas, you have x-axis, which is mole fraction of the gas or the solubility, and you have slope. Slope is given by, my dear students, m, which is actually also equal to tan theta, and this is equal to your KH value. This is equal to your KH value. Okay, so this is the graph which you can plot from this Henry's law. Perfect. Now let's move forward. You can write this. You can pause the video and write it. Now, my dear students, there are a few limitations. There are a few limitations for Henry's law, where it is applicable and where it is not applicable. Now, first, most important, I told you that I considered a dilute solution. And my dear students, Henry's law is actually applicable to dilute solutions only. What are dilute solutions? The solutions which have a lot of what? Your solvent. When you have a large amount of solvent that and very small amount of solute, that is your dilute solutions, and Henry's law is applicable to that only. See, Henry's law is applicable where the solution is dilute, and that is the reason I took moles of solvent much more than moles of solute. Okay, so this is what dilute means. Next, my dear students, it is applicable to less soluble gases. If you have gases which are very much soluble, then Henry's law is not applicable. So this is the limitation. To a very less soluble gases, Henry's law is applicable. Next, my dear students, at low pressure and high temperature, the gas behaves ideally. I hope you all remember the ideal gas, right? In ideal gas, you studied that low pressure and high temperatures, right? Yes. So at low pressure and high temperature, the gas behaves ideally and it is less soluble in the liquid, right? It will be less soluble because it is ideal, and ideal gases are not soluble in solutions, right? They're not soluble, basically. They are not liquefiable, actually. Ideal gases are not liquefiable. If you're trying to make a gas ideal, then it will be very less soluble. Henry's law can be applicable under this condition, okay? This is the condition where Henry's law is applicable. Last, my dear students, Henry's law can't be applicable. Henry's law can't be applicable when a gas chemically reacts with the liquid solvent. For example, NH3 in water. NH3 in water actually reacts. That is the reason that you cannot apply Henry's law. Henry's law is only applicable to gases which are very less soluble and they do not react to the solvent. Okay. So you need to know these limitations, because whenever the question is asked, it is asked from the limitations only. So pause the video and write these limitations. Let's move forward, my dear students. So now we'll do some questions and we'll understand the concept. Okay. So what you have to do is, you'll have to pause the video, you'll have to try the question yourself, and then you'll have to move forward. Okay. Check my answer, basically. Let's see what the question says. On increasing the temperature, the solubility of NaNO3 in water increases, decreases, or what? Given reaction is endothermic. This is the type of questions you're generally asked. So try to do this question yourself. It says that you have to tell the solubility of NaNO3. You know that you have a solute, you have a solvent, and this gives you a solution. And since the reaction is endothermic means delta H is positive, heat is absorbed, and if the heat is absorbed, here heat will be here. Okay, now on increasing the temperature, what are you doing? You're increasing the temperature. So if you're increasing the temperature, you're actually increasing the heat. If heat is increasing, this means that your reactant side is increasing. Lee-Chatelier principle will shift the equilibrium forward, right? Yes, in order to decrease the reactant concentration. So equilibrium forward, and if the equilibrium moves forward, then solubility actually increases, right? Yes, so your solubility increases. That is option A will be your correct answer. Option A will be your correct answer. I hope you're clear with this concept. Perfect. Now let's move forward, my dear students. The next question is on your screen. You have to try this question yourself. Try to do this question and then you will have to see ma'am's approach. Okay, perfect. Let's see what does this say. Which of the following is not a binary solution? So what is a binary solution, my dear students? Ma'am, binary solution was a solution which had two components. It had two components, right? It had two components, ma'am. One solute and one solvent. Now let's see which of the following is not a binary solution. Okay. Pure water and sugar. You have pure water and sugar. You have two components, so it is a binary solution. You have air. Air is a mixture, my dear students. You don't know how many gases are in air. You have N2, you have CO2, you have O2, you have methane, you have ethane. There are n number of gases in air, right? Yes. So this is not a binary solution. Let's see others. Mixture of benzene and toluene. You have benzene and you have toluene. It is a binary solution. You have ethanol and you have methanol. Mixture of ethanol and methanol, again ma'am, two components. So it is also a binary solution. Only one solution is not binary solution, and that is your air. So option B will be your correct answer, right? Yes. So this is how you are going to solve these questions. Let's move forward, my dear students. The next question is actually a PYQ on Henry's law. Okay, we'll be solving PYQs as well, so that we'll get some confidence that yes, we can do PYQs. Actually, they are asked very easy questions, so you have to solve this question yourself. What does the question say? It is a 2019 JEE question. Which of the following statements regarding Henry's law is not correct? And my dear NEET students, don't worry. You can solve this question as well. I'll always bring a question such that a JEE as well as a NEET student can attempt. Okay, so don't worry. You have to try this question. Try this question. Which one of the following statements regarding Henry's law is not correct? I hope you've found your answer. Now I'll help you out. Okay, first says different gases have different KH, Henry's law constant values at the same temperature. I know that KH depends on two major factors, temperature and nature of the gas. Temperature is kept constant, okay. But if I talk about different types of gases, they will have different KH values. So this is correct. I was asked which is not correct. So I have to tell which is not correct. The first statement is correct. Second, higher the value of KH at a given pressure. Now your pressure is constant. It is told that your pressure is constant, right? Given pressure means that your pressure is constant. Higher is the solubility of the gas in the liquid. Now my dear students, imagine you have pressure of gas is equal to KH into solubility. Now since this is constant, if you increase KH, then if you increase KH, then mole fraction has to decrease. That is, solubility has to decrease. Yes, ma'am. And it says that higher the value of KH, more the KH value, higher is the solubility. No, higher the KH value, lesser is the solubility. Lesser is the solubility. This means that this statement is wrong. This statement is Wrong. Clear? Perfect. Let's move to the third. The value of KH increases with increasing temperature. Yes, I told you the more the temperature, the more will be the KH value. And KH is a function of the nature of gas. Yes, different gases will have different KH values. It is a function of nature of gas. So this is absolutely correct. Fourth, the partial pressure of the gas in vapor phase, is proportional to the mole fraction of the gas in the solution. I told you the expression, partial pressure of the gas is directly proportional to the mole fraction of the gas. It is just defining this particular expression. The partial pressure of the gas in the vapor phase is proportional to the mole fraction of the gas in the solution. So this statement is also correct. So only one statement is incorrect, and that is your second statement. So option 2 is your correct answer. See, such an easy question was asked, right? Yes, you can do this question. If you want to write, and then we'll move forward. So now, my dear students, here is another question and you have to solve this question. Pause the video, try the question yourself, and then we'll move forward. Okay. So the question says 4 gases like H2, helium, CH4 and CO2 has Henry's constant values. You are given 4 different gases and you are given 4 different KH values. The gas which is more soluble in liquid, you have to tell the gas which is most soluble in liquid. So first I'll write all the gases. I'll write here gas, I'll write KH. Okay, you have H2, then you have helium, then you have CH4, and then you have CO2. What are the KH values? 16. Then it is 144.979. Then I have 0.413 and then I have 1.67. Right? These are the KH values. Now, I know that for a gas, right? Okay, now my dear students, you have to consider this as constant. So you can say that more the KH value, lesser will be the solubility. And you are asked the gas which is most soluble. So you need the maximum solubility. So if you need the maximum solubility of gas, you need the minimum KH value. So just see which gas has the minimum KH value. Which gas has the minimum KH value? CH4 has the minimum KH value. It will have the maximum solubility. So CH4, option B will be your correct answer. Such a easy question, right? Yes. Let's move forward then. If you want to write, you can write. Okay. You have a question. Compare KH value for H2 and SO2. Solvent is water. How are you going to do this question? So now, my dear students, here you have to just use a little of your concept. Okay. You have one gas H2 and you have one gas SO2, right? Yes. I have H2 gas, I have SO2 gas. I know that H2 is non-polar and I know that SO2 is polar in nature. Okay. So I also know that like dissolves like. I also know that like dissolves like. And I know that water, which is my solvent, is polar. Right? Yes. So if I see out of H2 and SO2, which gas will be more soluble? Which gas will be more soluble? SO2 will be more soluble in water. So I can say that solubility of SO2 is more. Right? Yes. Solubility of SO2 is more as compared to H2 solubility? Yes. Perfect. It says that you have to compare the KH values for both. Right? Yes. Now imagine, my dear students, I know that if your P of gas is equal to KH into solubility of gas and this is constant, then more the KH value, lesser will be the solubility. That is, they both are inversely proportional. If SO2 has higher solubility, right? If SO2 has higher solubility, then H2 will have lesser solubility. Right? Yes. So I can say that solubility, for solubility, SO2 is more than H2. If solubility of SO2 is more, then KH value of SO2 will be less as compared to H2. So Henry's constant KH value will be less of SO2 as compared to H2. So you can say that KH value for H2 will be more than SO2 as solubility of SO2 in water is more, right? Yes. So this is how you were supposed to do this particular question. I hope this is clear with you, right? Yes, you can write this and then we'll move forward. Let's move forward. You have another question. You have to try this question again, my dear students. Let's see. Match the following. You have to match the following. Okay. You have KH values and you have temperatures given. I know very clearly. First, try to do this yourself. Okay. Pause the video and try to do yourself. I hope you've done. You've paused the video. You've tried the question. Now, I know that KH depends on temperature, and the more the KH value, the more the temperature, the more will be the KH value. Right? Yes. Perfect. So first let's see. Let's write the temperatures in increasing order. Okay. 493 Kelvin, which is your E. Then it will be D. No. Then it will be B, which is 393 Kelvin. And then it will be D, which is 293 Kelvin. Okay. I know more the temperature, more the KH value. So you have to just write the increasing order of KH values. Write the increasing order. The maximum is for A, B, C, D, E. Let's write it as F, my dear students. Write it as F. Okay. This is F. So this will be F. I've written the temperatures. Now, the maximum is 0.3 for E. Then I have 0.2 for C. And then I have A, which is 0.1, right? Yes. So this will be the absolute matching. F with E, F with E, B with C, B with C, cross, and then D with D, yeah, D with A. This is how you have to match them. Easy, right? Yes. I hope you're clear with this. Please write this and then we'll move forward. You might have noted this. Now let's move forward. What are we going to do next? Next is your vapor. Okay, now we are going to start another topic, which is vapor. So now, my dear students, I want to ask you a difference. I want to ask you the difference between two terms. One is gas and the other is vapor. What is the difference between a vapor and a gas? Think about it, because this is the most important part which we will be understanding with this topic. We have two parts, two concepts, two words, two terms, that is gas and vapor. So what is the difference between them? You will just understand in the next 5 minutes. Now, what you have to do is imagine you have gas here. You have all the gas here. Okay, this is gas. Now, what you did, you applied pressure on this gas. You applied pressure on this gas. Okay. So when you applied pressure on this gas, the particles came closer. Now, what you did later, you actually removed the pressure. Now, when you removed the pressure, my dear students, what happened? Two things can take place. First is, if you remove the pressure, the gas particles again covers the whole surface. Okay, this is the first thing that can happen. What is the other thing that can happen? The other thing is, when you remove the pressure, all the gas has converted into liquid. All the gas got liquefied. All the gas got liquefied and it got converted into liquid, because you applied the pressure and the particles came closer to each other and they liquefied and you got the liquid, right? Yes. So this is your liquid and this is your gas. Now, what I want to make you understand here is that, my dear students, these two cases are possible. And this is the basic difference between vapor and gas. See, vapor is actually a part of a gas. Vapor is a part of a gas. Vapor is such a gas which can be liquefied. Vapor is such a gas which can be liquefied. Imagine you have a liquid, it got converted into its vapor, and now when you liquefy it, you will apply the pressure, it will get converted into its liquid. But there are some gases, let us talk about the ideal gases. The gases on which you apply how much pressure you want, it will not get liquefied at all. Those are the gases. So this is the major difference between a gas and a vapor. What is the major difference? A vapor is a special type of gas which can be liquefied, whereas a gas cannot be liquefied at all, right? So the difference is written here. Whenever a liquid evaporates, a vapor is formed, because you can apply pressure on that vapor and liquefy it and convert it into the liquid. Again, otherwise, vapor is a special state of a gas. It is a special state of a gas, right? Yes. So I hope this is clear with you. Very good, my dear students. Now, whenever anyone talks about this particular part, you will be thorough with this concept, right? Yes. Now let's move forward, and now we will study about vapor pressure. What is vapor pressure, my dear students? See, you can understand that, ma'am, what is vapor? Vapor is formed from a liquid. And whatever the vapor pressure, that vapor will exert pressure, we can call it as vapor pressure, right? Yes. The word in itself tells us the definition. Now we are going to understand that what is exact definition of vapor pressure. Now, you have a container here. You have a container here. What happens, my dear student, here is that you have some liquid here, right? Yes. This liquid gets converted into its vapor form. I'll write it with blue color. Pink color, okay? This vapor, this liquid gets converted into its vapor, and you know that this vapor will also get converted into the liquid as well, right? Yes. This is actually a state of equilibrium. Initially what happens, your liquid gets converted into vapors, and at some point of time the vapors start getting converted into liquid. Okay, so this is actually a equilibrium that takes place. We are going to understand this particular part. Okay, I hope you're clear with this. Now let's move forward, my dear students, and understand the basic difference between vapor, the basic term vapor pressure. For this, we need a container, closed container. Okay, so here we have a closed container. Okay, now what you have to do is, you have to understand, you have to think of a liquid here. Let's say this is the liquid here. Okay, see, this is the liquid, and you have liquid particles here. Okay, you have liquid particles present here. Okay, also you know that liquid particles will be present here as well, inside the liquid bulk, right? This is the surface part, and what is the bulk? Inside. So this is the bulk part. Okay, so I am talking about one particular particle, vapor particle, okay, liquid particle, and here also on the surface as well I am talking about one particular particle. So what you have to understand here is, my dear students, you have to understand it with a very interesting story. See, imagine this is a jail. Imagine this is a jail, and you have prisoners here, and there are some prisoners who are standing on the wall, who are actually standing on the walls, those barriers. They are standing on the barriers, and they are actually seeing the outside world. See, yes, these are the people, prisoners who are seeing the outside world as well, inside the jail, but they are inside the jail. Whereas these are some people who are inside the jail, and they are not worried about the world, they are not seeing the world, right? Yes. So now, my dear students, if we talk about this particular person, this person hasn't seen anything, right? He hasn't seen the outside world for a long time, so he doesn't have any longing of going outside, right? Because he does not know, he doesn't realize the difference between the outside world and the inside world. He's very happy here, he's very stable here, right? Yes, you understood this part. Now understand it with this liquid term. You have a liquid particle here, yes, and someone is applying force from this side. Some particle is applying force from this side, some particle is applying equal force this side, equal force this side. This means that this particular particle is balanced. If someone is pushing from this side, then the other person is pushing from this side and the force is balanced, right? Yes. So I can say that this is balanced. So it has less energy and it is stable. It has less energy and it is stable, right? I hope this is clear with you. Yes, ma'am. Perfect, my dear students. It was important to understand this because the particles which of a liquid which are in the bulk, they experience balanced force from all the directions, and that is the reason that they are balanced, they have less energy and they are stable. You know that in chemistry, when we talk about unstable things, they have a lot of energy. With the things which are stable, they have less energy. Okay. Now let's talk about a person on the surface. Let's talk about a prisoner on the surface. What will happen with this prisoner? See, this prisoner has seen the outside world. Yes, ma'am. And he knows that the people outside are so free and they can move here wherever they want. But I am stuck here. So this means that this prisoner actually wants to go outside because he has seen the outside world, right? Yes. So this prisoner is unstable. He is not stable. He is not happy being in the prison. He wants to go outside. He is unstable, right? Yes. Now let's understand it as a particle. It is a liquid particle which is on the surface, and since it is on the surface, it can experience a force from this side, experience a force from this side, this side, this side, this side, and this side, and this side. But it is experiencing unbalanced force because there is no one on the surface to give it a balanced force, right? Yes. This means that I can say that he is unbalanced. Right? So he is unbalanced, unstable, high energy, right? Yes, this particle has high energy, and the moment he will get a chance, he'll just go out in the outside world, right? Yes. So all the particles, not only this particle, in fact, all the particles on the surface are unbalanced. They are of high energy. See, now what happened? They all were just seeking for a chance to leave this prisoner. What happened? One day they got a chance. There were, let us say, the gatekeepers were not very attentive, and they just, the particle just went out from the prison, right? Yes, he escaped. So what can I say? That this particle escaped. Now, once the prisoner has escaped, he was in the prison for so long that now he is free. He wants to move all around, right? Yes. He'll be running this side. 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 He'll be running this side, right? Yes. He'll be running everywhere. He'll be like, I am free. I am going to go everywhere, right? Yes. But whenever the gatekeepers will realize that the prisoner is out, what will they do? They try to catch that person back, and they go and they try to catch that person back, and he comes back. Okay. What happened? He came back. Okay. But when the gatekeeper went to catch that prisoner, some other prisoner escaped. Let us say this prisoner escaped. Okay, so now he will go this side, he will go this side, he will go this side. Again the gatekeepers will realize. So this way, my dear students, slowly and slowly, more of the prisoners on the surface, that is more of the particles on the surface, will leave the surface, will leave the prisoner and go around, right? Yes. But you know that the gatekeepers will not sit still. They will catch the prisoners back again. So imagine slowly and slowly what happened. Let's say initially 5 prisoners went, then 10 prisoners went, and slowly some were coming back as well. So what happened? Let us say 100 prisoners left. Let us say 100 prisoners left. If 100 prisoners escaped and out of them 50 were taken back to the prison, still 50 were there, still 50 were outside, right? Now when they try to catch those 50, the other 50 will move, right? Yes, this is how at one particular time, what will happen at one particular time, there will be a time where equal number of prisoners will be leaving and equal number of prisoners will be coming back as well, right? Yes, that is a equilibrium will get attained. That is the equilibrium will get attained. That is, I can say that the rate of prisoners leaving the prison is equal to the rate of prisoners coming back to the prison, right? Now the same way you will understand this concept, that at one particular time all this is taking place at a T temperature which is constant. Okay, yes. So at one particular T temperature, what happens that when particles starts to leave the liquid and goes into the vapor phase, what are they becoming? They are becoming vapor. Yes ma'am, they are becoming vapor, and this process is known as evaporation. This process is known as evaporation. And my dear students, when they come back, what is that process known as? Condensation, right? Yes. So initially evaporation will take place. Yes. Slowly and slowly the gatekeepers will realize, and the particles will start coming back to the prison as well. That is the liquid surface, and that is known as condensation. So my dear students, at every temperature T, one point is reached where the rate of evaporation, that is the number of particles leaving the surface and getting converted into liquid, becomes equal to the rate of condensation. Okay, I'll just make you understand this. What can you say? You can say that initially your liquid started getting converted into vapor, right? Yes. And this process was known as evaporation. But after some T time, what happened? Those vapors started getting converted into the liquid as well, and this process was known as condensation, right? Yes. Now my dear students, at equilibrium, when an equilibrium will be achieved, what will happen? The rate of evaporation, that is the rate of particles leaving the surface, will be equal to the rate of condensation. You can write here that temperature is constant. Everything is happening at a constant temperature, right? Yes. So at equilibrium, rate of evaporation is equal to the rate of condensation, right? Yes. Now my dear students, at this dynamic equilibrium, the vapors which are in the particles which are in the vapor phase, they will definitely strike on the walls and they will exert some pressure. Yes. So the total pressure that is exerted at this dynamic equilibrium by the vapors is actually known as the vapor pressure. So what is the definition? Of vapor pressure? So what is the definition of vapor pressure? The definition of vapor pressure is the pressure exerted by the vapors at equilibrium at constant pressure is known as vapor pressure. And every gas, every liquid, in fact, every liquid has a constant vapor pressure at a particular temperature T. As long as the temperature is constant, that liquid will have a constant vapor pressure. Okay, so this is how you define a vapor pressure. What is vapor pressure? It is the pressure exerted by the vapors at constant temperature T. At the equilibrium condition. That is your saturated condition. I hope this is clear with you. You can write this and then we'll move forward. This is how the vapors are formed. This is how the equilibrium is attained, and at equilibrium the pressure exerted by the vapors is actually known as the vapor pressure. Okay, you can write this. Perfect. Now my dear students, I hope you're clear with this concept. Yes ma'am. Now what I want to tell you else other than this is, now I know the ideal gas equation, so you'll write from ideal gas equation. From ideal gas equation, we know that PV is equal to nRT. Okay, clear? Yes. Now let's move here. You see, I have kept the temperature constant. Since it is a closed container, my dear students, can I say that volume is also constant? Right? Yes. And when the equilibrium will be achieved, the number of vapors or the moles of vapors in the vapor state will be also constant, right? Yes, ma'am. So we can say that N, that is the moles of gas, will also be constant. I hope this is clear. We are going to use this concept here. See, my dear students, here N is the moles of vapor. Right? Yes. T is the temperature. V is the volume of container. Volume. I can write it as volume because the gas takes the volume. Right? Yes. And my dear students, R is your gas constant. It is a constant value. See, in these part, and P is your vapor pressure. P is your vapor pressure. Okay. Now imagine at equilibrium, my dear students, N, T, V are constant. See, and we know that R is a constant again. So P will be equal to nRT by V, which is equal to a constant value. So at one particular temperature, the vapor pressure of a gas is constant. So you can say that at constant temperature, vapor pressure of a liquid is constant. Okay, now you will be like, why ma'am? If we change the volume of the container, will the vapor pressure not change? As long as we are keeping the temperature constant, but we are changing the volume. So now you have to understand this concept, my dear students. What you have to understand here is that imagine you had a particular amount of gas. In this big container. Okay, in this big container whose volume was V. Here the number of moles of gas were N. Now imagine you shifted this into a small, let's take a bigger volume container, right? Let's say it was 2V volume, right? Yes. So you will have the same liquid will be same, my dear students. I hope you're clear with that. Yes, ma'am. If you have put in that liquid here, what will happen? Since the volume is more, more of the particles will get converted into the vapor phase. More of the particles will go into the vapor phase. So the moles of vapors would be 2N. And we know that P is equal to nRT by V. If this is 2 and this is 2 will be cancelled by 2. This means that always N by V ratio is constant. N by V ratio is constant, and that is the reason your vapor pressure is independent of volume and moles of gas. Okay, because if you will try to increase the volume, similarly your moles will increase. The ratio will always remain same. If you try to increase the moles, obviously the volume is increasing. That is the reason you can increase the moles, and again the ratio will be same. Since N by V ratio is constant, your vapor pressure is always a constant value. It only and only depends on the temperature. So the vapor pressure at a particular temperature is always and always constant. This is the most important part. So if you want, you can write this all and then we'll move forward. You've written this? My dear students? Perfect. You can write this if you want. Okay. With this, let's conclude today's session, my dear students. Right, we have studied a lot of things today, so you have to practice a lot of questions and you have to go through the theory as well, because theory is equally important. Conceptual questions are generally asked, so you have to make command on your topic. So I hope you understood each and every part in today's lecture. We'll cover next topic in the next lecture. I hope you're crystal clear with all the concept. Try studying very hard, because this is the best time you can make the best out of it. Okay, we'll meet in the next lecture. All the very best. Thank you so much.